Thank you, everybody, and good morning. With respect to the fact that many people here are just having their first, maybe in my case, second cup of coffee, I don't want to jump too far into artificial intelligence too fast for fear of getting a little bit vertiginous. So, Ashley, can you start us off with a little bit of a definition and a little bit of place setting? What is machine learning? And give us a sense of what the technology can accomplish now.
Okay, sure. Machine learning is essentially the process by which you can ask a machine to teach itself or to learn for itself from data. If you can program a machine to do something explicitly, you should do that, right? So when I got into computer science back in elementary school, it was programming the turtle in a Macintosh. And if what you need to do is take 5 steps, forward and 3 steps to the right, you can program that explicitly. But as we ask more of machines to do more and more complicated tasks, a lot of times now it's not possible to explicitly program them. And so machine learning is the process by which they can program themselves. The recent revolution in machine learning has really come from a convergence of big data sets that we can take advantage of, large, parallelized, computing infrastructure, so advances in computation, and then also new algorithms or new ways of training algorithms efficiently from large data. So I did bring a clip. We could take a look at it as an example of what this convergence has enabled. Okay, so this is a computer vision example. Obviously it's a neural network underneath. It's a convolutional neural network, a very complicated function approximator. So you can feed lots of data into their neural net, give it a goal, and it can learn, right? And so what we're seeing here, the data set that it takes advantage of to do this work is ImageNet, which is a very large collection of cat pictures and lots of different pictures on the internet. And different here than some other examples of this kind of research is the fact that the labels for these images are descriptions. And so basically what it does is it learns to describe, it looks at the way people describe these images and it learns to describe them. All right, so what it can do is it can take these low-level semantic attributes and describe new and novel objects using these attributes, maybe that it hasn't been trained explicitly on. So this is an example of what this convergence of technology could possibly enable.
I did note that it demarcated the plastic fruit as edible.
Yes.
That's an interesting sort of metaphor in there for both the potential of machine learning to recognize something that looks just like a banana as something that people would want to eat because most people would describe a fruit as edible, but also mischaracterizes that which any normal human would recognize as clearly plastic fruit, and notes it as edible. I mean, does that sort of place us sort of in our evolution of AI, that it is able to take a lot of really brilliant inputs, but maybe not make some of the inferences that a normal human being would in that situation?
Yes, and so it will learn what you ask it to learn. In this case, we didn't ask it to learn explicitly the difference between a banana. We didn't emphasize that. Learn plastic bananas from organic.
Yes.
But this does raise a point, right? Because I'm with the Johns Hopkins Applied Physics Laboratory. We're really trying to apply these technologies to critical challenges where these kinds of decisions really matter. Lives could be at stake, for example. And it brings us to kind of the edge of this technology, which is what mistakes, how good can it be in the real world where there's a lot of uncertainty? And how well can you understand ahead of time, how good it will be and how good it will generalize to new situations. So as we push forward, that's what we're really pushing on, how to make these more robust to the real world, which is kind of, uncertain.
Yeah. Naveen, I want to go to you. There's been a lot of fuss about neural net computer chips. And again, I want us to start this conversation off with a little bit of definition. What do these chips do? And I don't know if people have been following the news around NVIDIA and Intel, a lot of these companies that are manufacturing these chips. I mean, this is perhaps one of the most exciting products of 2017 in the tech space. What is all the fuss about? What do these chips actually accomplish?
Yeah, it is very exciting, especially from a technologist standpoint. It's like one of these rare times in history that you really see a real dramatic shift happen, right? And so what's happening, let me back up a little bit on what a neural network is first, maybe. Really, these are methods that have been around for a long time, and I would say deep learning, as people might have heard of, is is sort of the latest generation of neural network processing. And I'd say it's defined mostly by the learning rule we call backpropagation. And so there's many different flavors of deep learning. It's become sort of a very general class now of machine learning, actually. It's a subset. So it follows the same rules of machine learning where we have to learn from data. But one thing that's very interesting is it actually can extract compositional hierarchy. We were talking about this a little bit earlier from data. So, when you look at a face, we don't see pixels, we see eyes and noses and mouths and things like that. So it can actually extract that information from the data and learn it. So that's kind of one of the most exciting pieces of it. Now, breaking it down to what the fundamental computations are, instead of having lots of calculations that need to be sequentially sped up, right? I'm doing add these two numbers together, multiply this by another number, et cetera, et cetera, et cetera. Deep learning actually and neural networks are highly parallel. So the kind of processing you need is actually somewhat different. Instead of having something that can just blow through a bunch of instructions and in sequence very quickly, you actually want to deploy a whole bunch of them in parallel. And what's more is each one of those computations is much more lightweight. The type of computation is usually a multiply accumulate or a convolution. These are very simple operations mathematically.
Can you give me a concrete example of it? Take an industry or a job or any sort of occupational process, and explain how it existed both before this technology and how the technology could change it.
Yeah, I mean, something very simple, and not even an industry, is your cell phone, right? I mean, some of us probably use Siri or the Google Assistant today, and what's made it useful in the last few years is actually deep learning. It's basically allowed machine learning algorithms to take that next step and actually learn from more data and become performant to the point where they're rivaling or even beating humans, right? And I think that's really where a lot of this excitement has come in. So the example that was just shared with the convolutional neural net, that's a deep learning method, and the performance you're seeing there was just not possible before. So I think we had a lot of these methods kind of floating around in various ways before, but they just weren't to the point where they were useful yet. The concept was there, but we just couldn't actually, we were at 85% and we needed it to be 98%, sort of a thing. And so that's really what deep learning has done in terms of industry. So the excitement comes now that we can actually start reliably drawing inferences from data with these methods and actually change how we do operational processes or even new products, right? So, everyone of us probably uses Facebook or Google, these kind of things. Every one of the ads that's driven and information driven to you is actually now learned instead of just being sort of, here's the basic thing that everybody gets.
Well, you were saying this is something that people in the audience have probably experienced, something about auto-tagging people's faces, that there are certain inputs that say this is what Derek's face looks like, this is what Marie's face looks like, and so without the user tagging, the system knows exactly what the face looks like, and it can tag automatically before it has to.
And I think this is like the big sea change that's happening is that we want, instead of asking for information and getting an answer, now we're at a point where information is driven to us that is most relevant. And that's going to continue to get better and better and better with time.
Yeah. Marie, it's interesting because one of the dominant narratives to me of 2017 has been the scariness of big tech, whether it's Facebook and fake news or Google and its outsized profits.
Or killer robots.
I'm sorry?
Or killer robots.
Or killer robots. Let's never forget the killer robots.
We're all worried about that.
That there's this really fascinating interplay between both an awe that we have of tech and a fear that we have of it as well. And we were talking a little bit in the green room, and I asked you, do you think that the problem with AI in the short term is that as people are buying neural net computer chips and trying to create products with them, that consumers won't trust the AI, or that they'll trust it too much? Right.
And so my answer to that is first the one and then the other. Right? As with a lot of technology, initially we're very resistant to any sort of new thing. But once we get used to it, we're overly embracing of it and we overly trust it. And I think this is what happened with Facebook. Right? So initially people are like, Facebook, I don't know about that. That's not good. That's like not real people. But now we've all gotten, not everybody, but many of us have gotten pulled into that. And we're so comfortable with it and it's so familiar that we implicitly trust it, as though it's our familiar friend and it's Facebook and surely it couldn't be misleading us. And our friends are here and they can't be misleading us. And so we don't trust technology and then we trust technology too much. One of my concerns about the trend towards machine learning is just a need to be cautious about how we deploy these systems and the degree to which we can trust them and what they're actually doing for us. And in order to do that, we have to understand what's called machine learning bias. And bias is used in a technical sense in the machine learning community to talk about the nature of the sources of preference for one learned model over another learned model. And this can come from the sample data that you use, your training data that you use to train the system. It can also come from representational bias, which is the nature of the structures of the networks or the models that you're using. Some of the early speech recognition systems, for example, were very good at recognizing white, male, English-speaking voices, and not very good at recognizing women's voices, voices of people of color, voices of people with accents, because it hadn't been trained on that kind of data. And nobody was really thinking about that at the time. They were just excited that these systems started to work. But it took a little while before people realized, oh, wait a second, there's a limitation. And where is that limitation coming from? It's actually coming from the way the systems were designed and trained.
Right.
So we need to become more aware of those sorts of limitations, I think.
Right, and it's interesting.
One thing on that.
Sure, I wanted to just to attempt to summarize what you're trying to say is that the output is only as good as the input, right? That is, to a certain extent, these machines can do potentially wonderful things that we can't even begin to imagine. But as long as there are fundamental biases and mistakes with the computer scientists and the data sets that are being pushed into these products, they're going to have mistakes.
And what we're asking them to do, so plastic bananas.
Right, exactly.
Yeah.
I think, just to make it very concrete to everyone in the audience, this is not a new problem. It's called parenting, right? I'm a parent, so you want to expose your kids to a proper data set, right? I mean, it's been shown that children have more racist tendencies when they're adults if they grew up in a place that didn't see other people's faces, right? Same kind of thing happens in biological systems. So it's just to be very clear, like we do this in our daily lives with the little machines that are under our control.
No, this was a separate. I think it's exactly
They're a little
right.
under our control.
And I'm really happy.
Some amount of time.
I'm really happy you said that because if this was a separate conversation about sort of the state of America's sort of social policy and politics, I would say something to the effect of I think so many biases that exist among the public are essentially familiarity biases, whether it's sexism or racism or fears of immigration, that you see that so many of these biases on the part of individuals are also an input-output algorithm.
And these things we could have predicted these things, right? So Twitter and Facebook, and we have the psychology models and the social science models and the social networks models to say, oh, of course echo chambers are going to form. And of course stereotypes are going to be reinforced. And of course people are going to seek out information that reinforces their current beliefs, because that's what human beings do. But we weren't thinking about it when we designed and deployed the systems.
Yeah. I want to show both the dark side and the bright. I want to talk a little bit about the possibility of some of these technologies to make our lives better. Ashley, you were talking a little bit about some of the optic technology that you've been working on. Now that we've sort of established what machine learning can do now, push us a little bit farther into the future with specifically pointing to implications for healthcare, how these technologies can change our lives.
Yeah, sure. One of the things that, just to make people aware of what you can do with the technology we have today, I showed the computer vision algorithm, and we've actually been able to create a system that could restore sight for a blind person, and that was through a retinal prosthesis. This particular woman, she went blind as an adult, but her optic nerve still functions. And so with a retinal prosthesis, we can send electrical signals through the optic nerve and create, the sensation of sight. And so there's a goggle system that she can wear that gives her that, but the images are still very blurry. It's only about 60 pixels of sight. And so then the computer vision system, she can query it, and it can tell her about the objects she's seeing. So she can say things like, show me the remote. The optic nerve stimulation gives her the blurry object. The computer vision tells her which one is the remote.
Right.
And so that's a product that I believe will be available in the near future. The other thing we've done is, as we learn more about the brain, we're actually able to get neural integration of prosthetics. So for DARPA, we developed this robotic limb that's the most dexterous of its kind. And we showed through a neural implant that someone paralyzed from the neck down could control this to feed themselves a chocolate bar. But even going beyond that, and by the way, machine learning is critical to that. She's got basically electrode array on the surface of her brain reading those electrical signals and inferring the intent to move the arm. We don't know how to program that explicitly, so we need machine learning to help decipher those signals to infer the intent. Beyond that, we even showed that she could control non-anthropomorphic systems like fly a plane in a simulator through that interface. So I mean, imagine new ways for people that are paralyzed to be useful through interfaces like this, and that's with today's technology. And so I think going further, we have to figure out how to do that non-invasively. So she actually had a craniotomy. We had those sensors had to touch her brain to make that happen. Is there a way we can image through the skull to make that sort of neural interface possible? That's one of the research questions. But I think when we get there, there's amazing things that we can achieve.
Naveen, you're talking about technology that can make, say, a legal assistant 15,000 times more productive at reviewing legal documents. Ashley's talking about machine learning that can build an artificial eye, that can build an artificial nervous system, that can build an artificial arm. How far away are we from being able to build an artificial mind? A technology that is as advanced as the human mind, that an individual, perhaps someone who is brain dead, perhaps someone who has other cognitive deficiencies, can actually live through and use.
Really far.
Really far.
That's perhaps the Holy Grail from a sci-fi standpoint, but we're very, very far away from it. This is why some of the fears of robots taking over and things.
Singularity, right?
In my mind, it's a little comical because we're really far away from that. These are tools that allow us to sift through large data sets. That's what they can do, right? So what we can do today is kind of scale our abilities up. And so, like you said, this legal assistant, which can only read so many pages per hour, can now use a tool that can read 1,000 times more or 100,000 times more information and actually collapse that into some low-dimensional representation that we can now make use of. So that's what we can do today. Going to a fully autonomous agent in the real world that can act and reason and learn from its environment and not kill itself we're still very, very far away. Now I say that it's really hard, we're far away from it, doesn't mean it's not going to happen within the next 100 years, which I think it probably will.
So you think, right, but over a long enough time horizon, anything is possible in tech, I suppose, particularly when you're advancing at the speed of Moore's Law and doubling every 18 months in terms of productivity. But if I could, I'm not going to push back on that because I have no concept of when we're going to be able to build an autonomous human being. But I am interested in the question of what's the hardest part. If arms aren't that hard, and brains aren't that hard, and some elements of the nervous system aren't hard, and memory isn't difficult, memory's already been solved for essentially, and reading capacity isn't difficult, what are the hardest to solve elements of humanity for this technology?
Well, I'd argue that each one of those pieces are still very hard. So in the neural prosthetics world, for instance, it takes, the things are very experimental, they break, they're unreliable. To actually make something that works for a lifetime is just still very, very difficult. So every one of these things has a peanut buttering of problems that make it almost insurmountable at this point in time. Now, in terms of the machine learning side, if we abstract away all of these sort of physical problems and say, what's the problem with data? Why can't we make something that sort of draws the same kind of inferences as a human when you feed information to it? The human brain is really good at combining sort of the three basic paradigms of learning. We have supervised learning, unsupervised learning, and reinforcement learning.
And define those briefly.
Yeah, so supervised learning is when what we're showing here, where we have objects and you apply a label to it, or a face and you apply a name to it. So we have a large data set and we train on that, and it says, here's a new face, what's the name, right? So you're giving it the input-output. Unsupervised learning is where you're really looking for some sort of potentially useful structure in the data. So a baby learning, how to talk, right? Mm-hmm. We help it by saying da, these kinds of things. But in essence, it has to figure out the structure in the world from nothing, or from some very basal primitives that are it's imbued with at birth. And then reinforcement learning is kind of how you train your dog, right? It's like you did something good, here's your treat. So you reinforce the good behavior. And so brains are very good at combining all three of these in harmony. And so when a baby's learning how to talk, for instance, from having no baseline of that language, it has to use all three of these things. And we really haven't figured out how to do that. I mean, unsupervised learning is still this, this frontier that I think is not even, we haven't even scratched the surface. Reinforcement learning we're making a lot of inroads now. And I would argue that supervised learning we've almost solved in certain domains. So, each one of these things is huge in and of itself, and then combining them in a way that can actually sort of represent the real world is going to take some time.
So in a weird way, it's kind of the capacity for creativity in a way, the capacity of the system itself or the mind itself to draw inferences that weren't directly inputted. I mean, I've seen sort of music writing algorithms where you teach the machine sort of this is how A B C B sort of songs work. Now write your own music, and they do write their own music. It's terrible, but there at least is the element, at least, or the suggestion of unsupervised learning. Is that right?
So I think that you're right, except that we use so much creativity in our daily lives that we don't think about as creativity. And I think that what we might call common sense is actually what's still, for 60 years, we've been talking about how that's the hardest thing for artificial intelligence. It's the common sense, oh, that banana can't be eaten. Mm-hmm. I wonder what's going on here. Let me formulate some new hypotheses. Let me extend my representation. Let me think about the world in a little bit different way. Let me notice that I've had a failure of some kind, and maybe I can do better the next time. And that kind of autonomous, creative thinking about our daily interactions with the world, I think is something we just don't really have a lot of models for how to create these lifelong learning autonomous systems that are going to go out and learn about the world and transfer their knowledge from one situation to the next situation.
That's great. I wanted to ask you, Marie, what you thought about the job displacement implications of some of this technology. Some of the things that we've been talking about already, one could imagine how they would replace certain jobs, whether it's an office assistant being replaced by a technological assistant, or a law firm that they don't necessarily have to replace their entire paralegal staff, but if one paralegal can read as many or review as many documents as at whatever 15,000 times X before, maybe you don't need to hire the same number of paralegals that you did before the iPhone existed.
So I think what we've seen time and time again throughout history is that whenever there's a new technology, there's a huge job displacement. We don't need any more scribes. We don't really need bookkeepers anymore, right? The technology has displaced entire job categories, but every technology innovation has created even more jobs and even more kinds of things we can do. What I think we have to think about as a society, and what I think we have to choose, is how that's going to happen. Does that happen by chaos and people losing their jobs and entire communities of people who are starving and homeless and other people who are benefiting from the innovations? Or are we going to thoughtfully think ahead and say, who's going to be displaced? How can we help them? How do we educate them? How do we retrain them? How do we take the productivity that we've just created as a society and share it to everybody so that everybody gets to benefit from this instead of a few people who control the technology or who happen to be in the right place at the right time to benefit from the technology. So for example, one of the things that I just was reading an article, and I wish I could remember where I read it, that talked about how if we had more available workers and more available productivity, a huge potential is for more caregivers. Mm-hmm. That we have so many people in the world who could use physical and cognitive support, and we're not there yet with our technology.
Right.
I hope we'll get there. That's an area that I think we can really contribute towards, but we don't have enough caregivers, nurses, therapists, those kinds of jobs. We could have a lot more capacity to provide support for people to rebuild our urban infrastructure if we think about what are the right policies to help us make that shift.
In fact, the Bureau of Labor Statistics releases a forecast the next 10 years of job growth every 2 years. The last one came out about 2 weeks ago. And it said that just 2 job categories, home health aides and personal care aides will account for 10% of job growth in the next decade. So that goes directly to your point. But I wanted to ask you, Ashley and Naveen, also if you had any thoughts about the potential for either job displacement or job supplementing with machine learning technology.
Yeah, I mean, I think that in general, I think that we're best off not resisting, the advance of technology. As an algorithm developer, when I started my career, it was, what can I automate? And as you get further and further, you need more and more intelligent machines to automate things that you just don't want to do. And I think as a society, we ought to continue to move in that direction. What we can automate, we should. But I think as we talked about the limitations of artificial intelligence, 100 years was the number you threw out, and that resonates with my intuition as well. The real world is a messy place, and it takes the kind of internal representations, the really flexible internal representations we call intuition that we can apply to new problems. That right now is still uniquely human. So anything that where you have to be creative in dealing with creative problem solving, self-guided learning, self-evaluation as you're learning new tasks. These are still uniquely human. And so just in general, I think we ought to automate what we can and figure out how best to use the things that are still uniquely human to tackle the world's challenges.
Naveen, did you want a last word?
Sure. Yeah, I think the same kind of thing happened during the Industrial Revolution, as Marie was saying. I mean, you can read the articles back then, and some people were like hopeful because we're going to have our 10-hour work weeks, and other people are like, I'm not going to have a job. It's like the same kind of rhetoric happened at that point. And what really happened? Well, people actually worked more, and there were more employment opportunities. Now there are people who fix tractors and build tractors and design tractors and all this kind of stuff. So we're actually seeing a similar shift happening right now. I think there's some early data to suggest that yes, certain job categories are going away, but there are new opportunities created, right? I mean, data scientists right now there's just not enough supply, right? And that's changing. I'm seeing curriculum shifts in undergrad programs changing towards this, and I think in 5 years we're going to start filling that. And so we're seeing that shift happen in real time right now, and it's creating more opportunities, right? Yeah. We can do more productivity. It's an exponential curve. It's not linear. Right?
It's funny because the same BLS paper not only found that home health care aides and personal care aides would be the top two job categories the next decade, but also that the others were basically all in either healthcare or in computer science. And so the headline of the article that I wrote was that the future belongs to nurses and nerds. So thank you to the nerds, and thank you to you all for listening.